Several weeks ago at GTC, we announced our next generation GPU. It's called Volta, the new Tesla V100. Volta is an extraordinary technology undertaking. $3 billion R&D investment to create the processor, the software stack, the system, and all the tools on top of it. $3 billion. It's made here in Taiwan. Our collaboration with TSMC, based on TSMC's 12 nanometer FinFET, the collaboration we have with TSMC, I want to thank all of their engineers for such incredible work. It's really important to recognize that this chip, this GPU, is the largest processor the world has ever made. It is at the reticle limits of modern photolithography. You cannot make a chip any bigger. And then on top of that, we stacked multiple chips on top of each other using a TSMC process called CoWoS. So TSMC's 12 nanometer process, the CoWoS chip stacking technology, all integrated together, the world's largest single chip called the Tesla V100. 21 billion transistors, 5,000 CUDA cores, all came together to deliver 120 teraflops on one chip. 120 teraflops on one chip. Just to put that in perspective, that's like 250 CPUs. That's like 250 multi-core CPUs on one chip. Okay, it's just an extraordinary number of processors all packed together into one chip. So ladies and gentlemen, this is our next generation GPU called Volta. One of the most important innovations in Volta is we wanted to create a giant leap in GPU advance, but we also would like Volta to be the world's best TPU. Tensor operations is becoming more and more important. And so we wanted Volta to simultaneously be the most advanced GPU as well as the most advanced TPU. Excuse me. And so we introduced a brand new instruction. It's called the Tensor Core. New numerical formats and new instruction in CUDA. Every single generation, this is one of the really exciting things about CUDA, we can add more and more and more functions and features and instructions to CUDA, unlike a CPU which has a rather limited instruction set. And the reason why it's limited is because in our particular case, the way that CUDA was architected made it possible for us to continue to extend it. And we're now literally on CUDA 9. And so every single generation we can add more numerics, we can add more instructions, and continue to extend this modern computing instruction set, this modern computing architecture. This new CUDA Tensor Core has a tensor operation instruction, and it has a new numerics format. And it allows us to basically do one of the primitive, the most important elemental instructions of deep learning, which is basically linear algebra. TensorOp allows us to take a 4x4 matrix, multiply by another 4x4 matrix, and add a 4x4 matrix all at one time. All at one time. And so the way you think about linear algebra, the two 4x4 matrices, each one of the columns has to be multiplied by the row, and you add all those numbers together. Okay, so 4 multiplies and 4 additions results in one new element into the matrix. And then after that, you do another 4x4 addition. That combination is all done at exactly the same time. And we also have the ability to mix precisions. So the A times B, the A, for example, could be an activation, the B could be a weight, and the C could be the bias from the stochastic gradient descent. Okay, from the back propagation. This is done in FP16, B is done in FP16, and we add FP32. As a result of that, we can achieve simultaneously very high performance and very high precision. That's one of the great breakthroughs of the Volta Tensor Core. Let me show you how we did it on Pascal. And so you could, as I was describing earlier, the green is one 4x4 matrix. The purple is another 4x4 matrix. We're going to multiply those two 4x4 matrix, and it's going to create one result at a time that we're going to add into the final result. Okay. And so the way we solve that is literally one row and one column at a time, one row and one column at a time, and then we add it all together. The way that we do it in Volta is a little bit faster. This is the way we do it on Volta. And this is in one CUDA core. We do this 5,120 other times. And so the challenge is this. When you think about 120 teraflops, the question is, how do you keep the data moving through the processors? The memory hierarchy, the memory throughput, all of the thread parallelism that we have to sustain is at a level that the world has never seen before. The amount of energy efficiency techniques that we have to bring to bear so that we can keep the power very, very efficient is like nothing's ever been done before. And so as a result, the Tensor Core operation is able to achieve 12 times what Pascal was able to achieve in the past. So ladies and gentlemen, Volta with the new Tensor cores.